Imagine a world millions of years before the first hominid shaped a stone tool, a planet cloaked in vast ancient seas and primeval forests, its skies perhaps alive with unfamiliar atmospheric compositions. Within this deep geological epoch, unobserved by any future human eye, could the shimmering towers of a lost civilization have reached for the sun? Everything we think we know about the timeline of intelligence on Earth might be fundamentally incomplete. What if humanity is not the first, but merely the latest inheritor of this planet, preceded by an advanced industrial species whose very existence has been utterly erased by the relentless march of geological time? The stakes of such a revelation are profound. It would redefine our understanding of life's resilience, the cycles of planetary habitation, and even the ultimate fate awaiting our own technological era. This isn't a fantastical tale of ancient astronauts, but a rigorous scientific inquiry, challenging the deep-seated assumption that our species represents Earth's singular moment of technological awakening. This is the essence of the Silurian Hypothesis, a thought experiment transformed into a scientific detective investigation, asking what enduring fingerprints a non-human industrial civilization, active tens of millions of years ago, might have left behind in the planet's silent archives. The fleeting lifespan of a technological society, measured in thousands of years, is but a blink against the colossal backdrop of Earth's 4.5 billion year history. In this documentary, we embark on that very investigation. We will explore the subtle yet unmistakable traces such a civilization could have etched into the geological record, from anomalous isotopic ratios in ancient rock formations and the potential for long-lived technofossils like plastics, and even the chilling long-term consequences of an ancient nuclear conflict. If you are ready to challenge your assumptions about life, intelligence, and humanity's place in the cosmic timeline, hit that like button and subscribe to Terran for more journeys into the unknown. Prepare yourselves, we begin. Our concrete cities and towering monuments might seem like indelible marks upon the Earth, destined to stand for millennia, perhaps even etched into the planet's very memory. Yet, against the titanic scale of geological time, even the most formidable human constructions are mere dust motes, ephemeral blips in an expanse stretching across billions of years. This fundamental mismatch in timescales is the central challenge to the Silurian Hypothesis, the formidable obstacle to finding any evidence of a pre-human industrial civilization. Earth itself is an architect of erasure, a planetary shredder constantly recycling its surface, burying, melting, and reforming its own history. Consider the immense backdrop against which any ancient civilization would have played its part. Earth is approximately 4.4 billion years old. Our entire written history spans roughly 5,000 years. The Industrial Age, which began to leave truly global, unambiguous traces, is barely 2 centuries old. If we were to compress Earth's entire history into a single 24-hour day, human civilization would blink into existence for the last few hundredths of a second. Even the reign of the dinosaurs, a staggering 165 million years, occupies only about an hour and a half on this cosmic clock. A civilization existing, say, 100 million years ago, would have lived and died in a fraction of that time, leaving behind a legacy that would then face an additional 100 million years of relentless geological assault. The primary culprit in this grand erasure is plate tectonics. Earth's outer shell is not a static surface, but a dynamic mosaic of colossal plates constantly grinding against each other. Continents drift, oceans open and close, and vast swathes of the Earth's crust are inexorably dragged back into the planet's molten mantle at subduction zones. Any remnants of a civilization, its cities, its infrastructure, its waste dumps, situated on oceanic crust would be completely subducted and melted within a few 100 million years, perhaps even tens of millions. The oldest oceanic crust existing today is only about 200 million years old, a mere blink in the planet's lifespan. Continental crust is more stable, but it too is subject to immense forces. Mountain ranges are thrust upwards, only to be eroded away into plains, their constituent rocks resedimented into new layers, often miles from their origin. Erosion and weathering are equally relentless forces, operating on scales that defy human comprehension. Wind, water, and ice constantly abrade the land, grinding down mountains, carving canyons, and transporting sediment across vast distances. Rain dissolves soluble minerals, rivers carry trillions of tons of material to the sea each year, and glaciers act as colossal bulldozers, scouring landscapes down to bedrock. Over millions of years, a city built of even the most durable materials would be slowly dismantled, its components dispersed and broken down into their fundamental constituents. The familiar skyline of a metropolis, designed to defy gravity and time, would become an indistinguishable layer of mineral grains, scattered across ocean floors or buried beneath new geological strata. Then, there is the rock cycle itself, a planetary metabolism that ensures nothing truly remains unchanged. Sedimentary rocks, formed from accumulated layers of eroded material, are buried, heated, and compressed, transforming into metamorphic rocks. These, in turn, can be melted into magma and later solidify as igneous rocks, only to be uplifted, eroded, and begin the cycle anew. Each phase of this cycle acts as a filter, destroying or profoundly altering any fragile artifacts or chemical anomalies left behind by a civilization. A skyscraper of steel and concrete, if somehow preserved long enough to be buried, would eventually be metamorphosed into a jumbled mass of new minerals, its intricate structure utterly obliterated by unimaginable pressures and temperatures. Even the process of fossilization, which preserves biological organisms, is incredibly rare and highly selective. Only a tiny fraction of all life that has ever existed leaves any fossil record, and usually only under very specific conditions: rapid burial, anoxic environments, and the presence of hard body parts. Industrial artifacts, even durable ones, are not organic in the same way, nor are they typically found in environments conducive to long-term preservation. A plastic bottle in a landfill today might degrade into microplastics in centuries or millennia. But a plastic bottle from 50 million years ago, it would have faced the crushing weight of overlying rock, exposure to groundwater, heat, and seismic activity, all conspiring to break down its complex polymers into simpler, indistinguishable organic compounds. The geological record, therefore, is not a complete library of Earth's history, but a heavily edited, fragmented, and often rewritten palimpsest. What we find are snapshots, brief moments captured and preserved, often in isolated pockets, within a story spanning eons. The vast majority of any given epoch is simply lost to us, chewed up and spit out by the planet's ceaseless activity. This profound bias towards destruction means that any evidence we seek must be either incredibly robust, extraordinarily pervasive, or leave a signature so unique that it stands out even after millions of years of reprocessing. This immense scale of erasure also impacts our very definition of what constitutes trace or evidence for the Silurian hypothesis. We cannot expect to find intact cities or recognizable tools. Instead, our scientific detective work must pivot to seek signals at a planetary level, anomalies in the Earth's chemistry that defy natural explanation. We are looking for something that could survive the grinder, something that might even be created by the grinder itself, through the deep burial and eventual resurgence of materials. The signatures we seek must be capable of persisting through cycles of rock formation and destruction, weathering the storm of geological time. This is precisely why the search for subtle chemical deviations, rather than obvious artifacts, becomes our primary tool. The very mechanisms that hide civilizations might also be the ones that, paradoxically, preserve their most fundamental chemical legacies, albeit in forms almost unrecognizable to the untrained eye. It is within these deep time archives, transformed and diffused, that the faint echoes of a pre-human industrial age might still reside, patiently awaiting discovery. The relentless grinder of geological time ensures that grand structures crumble, and even the most resilient artifacts are eventually reduced to dust. But while stone may erode and metal corrode, the fundamental atomic composition of our planet holds a more enduring memory. For the scientific detective investigating the Silurian hypothesis, the trail of physical ruins is likely cold, utterly erased. The true clues, therefore, must lie in the subtle planetary scale shifts within Earth's chemistry, the isotopic anomalies that act as an enduring chemical fingerprint of industrial activity. To understand this, we must first grasp the concept of isotopes. Every element is defined by the number of protons in its nucleus. However, atoms of the same element can have different numbers of neutrons, resulting in variations known as isotopes. For instance, carbon always has 6 protons, but it can have 6, 7, or 8 neutrons, giving us carbon-12, carbon-13, and carbon-14 respectively. While these isotopes are chemically identical for most reactions, their slight mass differences mean that natural and industrial processes can sometimes preferentially select one over another, leading to a phenomenon called isotopic fractionation. This subtle preference leaves a signature, a deviation from the natural isotopic ratios, which can persist long after the original materials have vanished. A prime example of such a planetary scale signature stems from the burning of fossil fuels. These fuels, coal, oil, and natural gas, are derived from ancient organic matter, the remains of plants and animals that died millions of years ago. When living organisms perform photosynthesis, they preferentially take up the lighter carbon-12 isotope from the atmosphere over the heavier carbon-13. Consequently, fossil fuels are naturally depleted in carbon-13. An industrial civilization, extracting and burning vast quantities of these ancient carbon reservoirs, would release this carbon-13 depleted carbon dioxide into the atmosphere. This influx would subtly but measurably alter the global carbon isotopic ratio, specifically lowering the C13 to C12 ratio in the atmosphere, oceans, and subsequently in carbonate rocks and organic matter that formed during that period. Such a global, sustained perturbation would be an unmistakable signal, a telltale marker of widespread combustion on an industrial scale. Beyond carbon, other elements offer equally compelling avenues for investigation. Nitrogen, a fundamental building block of life and agriculture, also exists in various isotopic forms, primarily nitrogen-14 and nitrogen-15. Natural processes, like bacterial nitrogen fixation, tend to produce a specific range of N15 to N14 ratios. However, the production of synthetic fertilizers, a cornerstone of modern industrial agriculture, relies on processes like the Haber-Bosch method, which can introduce distinct nitrogen isotopic signatures into the environment. Large-scale application of these artificial fertilizers would alter the nitrogen cycle, enriching or depleting specific nitrogen isotopes in soils, sediments, and even ancient ice cores should they survive. Detecting a sudden, widespread shift in the nitrogen isotopic composition within a specific geological layer could point towards an agricultural revolution driven by a pre-human industrial society. Sulfur isotopes provide yet another potential chemical fingerprint. Sulfur, a common element in Earth's crust, is released into the atmosphere during volcanic eruptions and by various biological processes. But industrial activities, particularly the smelting of ores and the burning of fossil fuels containing sulfur, release sulfur dioxide. This industrial sulfur, often derived from specific geological deposits, can have a distinct isotopic signature, e.g., changes in the S34 to S32 ratio. If a civilization engaged in extensive mining and industrial processing, these anomalous sulfur emissions would deposit into sediments, oceans, and ice sheets, leaving a persistent record of industrial-scale atmospheric pollution. Such a signal would be distinct from natural volcanic activity, which often leaves a different, though also measurable, isotopic signature. The challenge, of course, lies in the preservation and detection of these ephemeral signals across millions of years. While the planet's surface is constantly being reworked, ocean sediments act as vast, relatively undisturbed archives. Layers of sediment accumulate slowly, year after year, century after century, encapsulating traces of the atmosphere and ocean chemistry at the time of their deposition. These sediments, particularly those in deep anoxic basins, can preserve organic and inorganic compounds, including the isotopic ratios of elements, with remarkable fidelity over immense timescales. Scientists routinely drill cores from these ocean floors, extracting columns of sediment that can represent hundreds of millions of years of Earth's history, layer by undisturbed layer. Each layer is a page in Earth's deep time diary, waiting to be read. Beyond deep-sea sediments, certain types of rock formations can also serve as long-term repositories. Sedimentary rocks, especially shales and limestones, form from compacted layers of mud, silt, or calcium carbonate, often locking in the chemical composition of their environment. Similarly, some ancient ice cores, if conditions were right for their formation and preservation from a glacial period, could offer pristine atmospheric samples. The stability of isotopic ratios within the crystalline structures of minerals means that if these anomalies were sufficiently widespread and embedded into the geological record, they could potentially survive diagenesis, the physical and chemical changes that sediments undergo after deposition and during burial, and even mild metamorphosis. The key is to look for a global anomaly, a consistent pattern across multiple geographically separated sites, rather than an isolated, localized event that could be attributed to natural geological processes. The search for these anomalies requires sophisticated analytical techniques. Geochemists use mass spectrometers, instruments capable of precisely measuring the ratios of different isotopes within a sample. By analyzing thousands of samples from different geological epochs, they build a baseline, a record of Earth's natural isotopic fluctuations. Against this natural ebb and flow, a sudden, sharp, and globally coherent deviation in the isotopic ratios of carbon, nitrogen, or sulfur would stand out as an undeniable testament to a planetary scale industrial event. It would be an outlier so statistically significant that it could not be explained by volcanoes, asteroid impacts, or any known natural cycles. This detective work demands patience and meticulous precision. Scientists would need to define the exact geological period under investigation, for example, the Silurian period itself, or perhaps the Cenozoic era, and then systematically sample and analyze rock and sediment cores from around the world that date to that specific time frame. They would look for a sharp increase in carbon-12 depletion, a sudden shift in nitrogen, 15 enrichment, or peculiar sulfur isotopic ratios that do not correlate with known natural events. The absence of such signatures would not necessarily rule out a past civilization, as the Grand Erasure is powerful, but their discovery, a pronounced and undeniable isotopic anomaly of industrial character, would be one of the most profound scientific findings in human history, forcing a radical re-evaluation of Earth's past and our own unique place within it. It would reveal that we are not the first to gaze upon these stars and ponder the universe, but rather stand on the shoulders of forgotten giants. While isotopic anomalies offer a planetary-scale chemical whisper of a past industrial civilization, the concept of technofossils delves into the possibility of finding more direct, albeit highly transformed material evidence. If a pre-human industrial society existed, it would have produced novel synthetic materials just as our own civilization has. The challenge, of course, lies not just in their creation, but in their extraordinary persistence against the geological grinder for tens or hundreds of millions of years. The most obvious candidate for a technofossil in our own era is plastic. Plastics are synthetic organic polymers, materials engineered by humans not found in nature. They are celebrated and reviled for their durability, their resistance to decomposition by natural biological processes. On human timescales, plastics can persist for centuries, sometimes even millennia, in landfills and oceans. Our modern world is leaving behind an indelible plastic layer in the sedimentary record, a clear marker of the Anthropocene epoch. Could a similar ancient layer of synthetic polymers exist, buried deep within Earth's crust? However, the durability of plastics is relative. While resilient against microbial degradation or simple weathering over decades, their longevity drastically diminishes when confronted with geological forces operating over millions of years. Exposure to high pressures and temperatures during burial, the corrosive action of groundwater, the relentless movement of tectonic plates, and the sheer chemical instability of long-chain polymers under such conditions would eventually break down even the most robust plastics. They wouldn't remain as intact bottles or bags. Instead, they would likely degrade into their constituent monomers, fragment into microplastics, or even chemically alter into simpler, more thermodynamically stable organic compounds that might be difficult to distinguish from natural bitumen or kerogen. Yet, this degradation isn't necessarily a total erasure. Even as macroscopic plastic objects disappear, their chemical ghosts could persist. Microplastics, tiny fragments less than 5 millimeters in size, are already ubiquitous in modern environments permeating soils, oceans, and even the atmosphere. These microscopic particles can be incorporated into accumulating sediments, where they might survive longer than larger objects by virtue of their sheer number and smaller surface area to volume ratio. making them less susceptible to some forms of chemical attack. The challenge for detection in ancient rock would be to find these microscopic, often chemically altered particles and unequivocally identify them as artificial. Techniques like Fourier transform infrared spectroscopy, FTIR, or Raman spectroscopy could potentially identify specific polymer residues by their unique vibrational signatures, even after extensive degradation, provided the chemical structure hasn't completely randomized. Beyond plastics, an advanced civilization might have produced other synthetic materials with even greater geological resilience. Consider ceramics or specialized glass compositions, particularly those manufactured at extremely high temperatures or with unique elemental dopants that don't occur naturally. While natural ceramics like clay pots degrade relatively quickly, advanced industrial ceramics designed for extreme durability and heat resistance could potentially persist for much longer, embedded within geological formations. Similarly, concrete and other cementitious materials, while subject to chemical alteration over geological epochs, leave behind distinct mineral assemblages that could, in theory, be identified. A layer of cement clinker minerals or unusual aggregates within ancient sedimentary rock could signify large-scale construction. The detection of these technofossils would involve an intensive interdisciplinary search. Geochemists and material scientists would need to analyze samples from ancient sedimentary basins, particularly those known for exceptional preservation, such as deep-sea anoxic sediments or undisturbed lacustrine lake deposits. They would employ techniques like scanning electron microscopy to search for microscopic structures with unnatural geometries or compositions. X-ray diffraction could identify crystal structures unique to synthetic materials. And sophisticated organic geochemistry, using gas chromatography mass spectrometry, GCMS, could hunt for complex synthetic organic molecules or their specific degradation products that bear no resemblance to known natural biochemical pathways. The key would be to identify patterns of these materials, their distribution, concentration, and unusual chemical makeup that strongly suggest artificial origins rather than natural processes. A significant hurdle is distinguishing truly artificial materials from naturally occurring analogues or complex organic matter. Earth's geochemistry is incredibly diverse, and many natural processes can produce compounds that, at first glance, might seem unusual. Therefore, a technofossil would not just need to be unnatural, but definitively synthetic. This requires a deep understanding of natural geological and biochemical baselines for the specific epoch being studied. For example, if a peculiar carbonaceous residue is found, its carbon isotopic signature, linking back to Block 2, might provide the crucial evidence for its synthetic origin, differentiating it from natural organic deposits. The presence of elements in unusual concentrations or combinations, or a distinct lack of biological precursors, could also serve as discriminators. The sheer scale of a civilization's industrial output is also a critical factor. For technofossils to be detectable millions of years later, they cannot be isolated curiosities. They would need to have been produced in sufficient quantities to form a widespread geological layer, a global scar on the planet. Our own Anthropocene provides a powerful model. The distinct layers of plastics, concrete, aluminum, and other synthetics are becoming globally pervasive, forming a future marker horizon. If a Silurian civilization had a comparable industrial footprint, distributed globally through ocean currents and atmospheric transport, then its technofossils might be buried across multiple continents, offering a statistically significant signal. The deep ocean floor, particularly subduction-resistant areas, could be a prime hunting ground. While much oceanic crust is recycled, some sediments remain relatively undisturbed for vast periods. Rapid burial in anoxic conditions, which prevents oxidation and biological degradation, could encapsulate and preserve altered synthetic materials or their chemical residues over long timescales. Even if the original polymer structure is completely lost, the resulting complex organic molecules could bear a specific molecular fingerprint that is inconsistent with any known natural process. The search, therefore, is not for an intact relic, but for a highly processed, deeply buried, and chemically modified signature of artificiality, a ghost in the machine of Earth's ancient crust. This is a quest for the ultimate chemical needle in the planet's oldest haystacks. Beyond the direct chemical whispers of industry, and the elusive ghosts of technofossils, a pre-human civilization much like our own would almost certainly have faced the fundamental challenge of feeding its population. Large-scale industrial societies require agriculture capable of supporting millions, if not billions, of individuals. This necessity leads our scientific investigation to a crucial question. What enduring geological signatures could massive, ancient agriculture, particularly through the use of synthetic fertilizers, have left behind? Our current civilization's food production is inextricably linked to the Haber-Bosch process, a technological marvel that synthesizes ammonia from atmospheric nitrogen, forming the backbone of modern synthetic fertilizers. Before this innovation in the early 20th century, humanity relied on natural sources like guano or limited nitrogen-fixing crops. The Haber-Bosch process allowed for an unprecedented increase in food output, fundamentally altering the global nitrogen cycle. This massive injection of fixed nitrogen into terrestrial and aquatic ecosystems leaves a distinct, global geochemical imprint, one that a Silurian civilization might have mirrored. The most direct trace would be a dramatic and sustained shift in nitrogen isotopic ratios, as discussed in our previous block. While natural processes like lightning strikes and biological nitrogen fixation convert atmospheric nitrogen into usable forms, they do so with specific isotopic preferences. The industrial synthesis of ammonia, however, can produce nitrogen with a different, often more uniform isotopic signature. A sudden, widespread, and sustained increase in, for example, a depletion of nitrogen, 15 relative to nitrogen-14 in ancient sediment layers, could be a strong indicator of industrial-scale nitrogen fixation for agricultural purposes. This signal would need to be global, appearing in marine and terrestrial sediments across different continents, and clearly distinguishable from natural background variations in the nitrogen cycle. But the use of synthetic fertilizers goes beyond just isotopic shifts. The runoff from heavily fertilized agricultural lands introduces massive amounts of nitrates and phosphates into rivers, lakes, and oceans. This nutrient loading, known as eutrophication, can lead to algal blooms, which upon dying deplete oxygen from water bodies, creating anoxic or hypoxic zones. These dead zones are characterized by a unique sedimentary signature, layers rich in organic carbon and depleted in oxygen-sensitive minerals. While natural anoxic events occur throughout Earth's history, a sudden, widespread, and synchronous appearance of such dead zones globally, particularly if correlated with other industrial markers, would be highly suspicious. The extent and synchronicity of such events would be key to differentiating them from localized natural phenomena. Furthermore, the very act of large-scale agriculture transforms landscapes. While physical structures erode, the geological impact of widespread soil erosion, terracing, or irrigation systems, if extensive enough, might leave subtle geomorphological or sedimentary traces. For instance, accelerated soil erosion from large-scale cultivation could lead to increased sedimentation rates in adjacent floodplains or coastal areas, visible as unusually thick, fine-grained sedimentary layers. While difficult to distinguish from natural erosion events, a global pattern of such increased sedimentation, occurring alongside other chemical anomalies, would add to the circumstantial evidence. The long-term impact of artificial nutrient loading could also alter the composition of ancient marine ecosystems, leaving fossilized evidence. For example, specific species of algae or bacteria that thrive in high nutrient conditions might suddenly proliferate, leaving a distinct microfossil record. Paleontologists could analyze deep-sea microfossil assemblages for abrupt, widespread shifts in species dominance or diversity that correlate with suspected agricultural periods. The fossil record, though incomplete, can still tell tales of ecological upheaval. The search for these agricultural technosignatures would require a multi-proxy approach, combining isotopic analysis with sedimentology, paleontology, and geochemistry. Scientists would drill sediment cores from various marine and lacustrine environments, meticulously analyzing each layer. They would look for a synchronous increase in specific nutrient proxies, like phosphate or nitrate concentrations, accompanied by shifts in nitrogen isotopes, and potentially, microfossil evidence of altered ecosystems. The sheer scale and global distribution of such a signal would be paramount. Another aspect of industrial agriculture is the potential for bioengineering or the large-scale domestication of species. While direct genetic evidence from millions of years ago is virtually impossible to recover due to DNA degradation, an ancient civilization might have left a fossil record of domesticated flora or fauna that exhibit unusual characteristics or a sudden, widespread appearance outside their natural range. For example, a fossilized plant species showing signs of artificial selection for increased yield, or the widespread cultivation of a species far from its evolutionary origin, could be an intriguing, albeit highly speculative, clue. This would require careful paleontological comparison with known natural plant and animal evolutionary pathways. The challenge, as always, lies in overcoming the grand erasure and distinguishing artificial signals from natural geological events. Earth has experienced many episodes of natural climate change, mass extinctions, and shifts in biogeochemical cycles that can mimic some aspects of industrial activity. For instance, large-scale volcanic eruptions can release vast amounts of CO2 and sulfur into the atmosphere, impacting climate and ocean chemistry. However, these natural events often have distinct geological signatures, e.g., specific ash layers, basalt flows, or unique geochemical markers, and different isotopic profiles compared to industrial emissions. The key is to look for a combination of signals that collectively point towards a complex technological origin rather than any single natural phenomenon. The scientific methodology would involve establishing robust baselines for natural nitrogen, phosphorus, and carbon cycles over millions of years preceding and following the suspected civilization's era. Then, researchers would hunt for statistically significant deviations from this baseline that are consistent with industrial-scale activity. This is a scientific equivalent of archaeological excavation, but instead of digging for pottery shards, we are sifting through billions of years of planetary chemistry for the subtle global echoes of ancient farms and factories that fed a forgotten world. The potential discovery of such a widespread, industrial-scale agricultural signature would rewrite not just human history, but the history of intelligent life on Earth. While the isotopic anomalies of industrial emissions and the faint echoes of synthetic materials hint at the productive capacity of a pre-human civilization, there exists a far more chilling and enduring signature: the planetary scar of nuclear conflict. The consequences of an ancient nuclear war, waged millions of years ago, would leave behind a distinct and terrifying imprint in the geological record, a signature of ultimate self-destruction that even the grand erasure of time might struggle to completely obliterate. This grim possibility leads our scientific detective work into the realm of radioactive isotopes and the unique chemical fingerprints of atomic fire. A full-scale nuclear exchange, even if relatively primitive by today's standards, would inject massive amounts of radioactive isotopes into the atmosphere. The most prominent and long-lived of these would include elements like cesium-137, strontium-90, and iodine-131, but also crucially plutonium and specific fission products. While the shorter-lived isotopes would decay rapidly, the longer-lived ones, particularly the transuranic elements like plutonium-239, with a half-life of 24,100 years, could potentially leave residual evidence, though diluted, in ancient sediments. However, the most definitive and persistent signature would come from the ratios of these isotopes and the creation of novel, non-natural isotopes. The primary evidence would manifest as a sudden global spike in certain fission products that do not occur naturally in such concentrations or ratios. For instance, the ratio of plutonium-244 to plutonium-239 is a key indicator. Plutonium-244 is an extremely rare primordial isotope. Its presence in the early solar system almost entirely decayed away by now. Any significant spike of Pu-239 in the geological record, especially if accompanied by other fission products like cesium-135 or technetium-99, would be a strong indicator of anthropogenic or archaeoanthropogenic nuclear activity, fundamentally different from natural background radioactivity, or even the trace amounts from natural nuclear reactors like Oklo. The key here is the isotopic signature of nuclear fission, the distinct suite of elements and their specific ratios produced by splitting heavy atomic nuclei. Such an event would also inject vast quantities of fine dust and soot into the stratosphere, triggering a nuclear winter scenario. This global shroud would block sunlight, causing a rapid and dramatic drop in global temperatures. This sudden climate perturbation would leave its own mark, a distinct layer of iridium-rich soot and charcoal particles, distributed globally in sediment layers. While iridium is famously associated with asteroid impacts, a nuclear winter signature would differ significantly. An asteroid impact typically leaves a singular, sharp iridium anomaly, often accompanied by impact ejecta, shocked quartz, and microtectites. A nuclear event, however, would produce a widespread soot layer, enriched in unusual elemental ratios and lacking the telltale impact minerals. The iridium, if present, would likely be mixed with other metallic dusts from the vaporization of cities and infrastructure. The atmospheric effects of an ancient nuclear war would also reverberate through the planet's atmospheric chemistry. Massive amounts of nitrogen oxides, NOx, would be produced in the fireball and subsequent atmospheric reactions. These nitrogen oxides would deplete the ozone layer, leading to a surge in harmful ultraviolet radiation reaching the Earth's surface. This ozone depletion could be indirectly detected through proxy records in ancient sediments. For example, a global increase in UV-resistant spores or a sudden decline in UV-sensitive marine organisms correlated with other nuclear signatures could be indicative. Furthermore, the fallout itself would deposit novel radionuclides and altered soil chemistry into terrestrial environments and ocean basins. Ancient soil samples or deep-sea clays could, in principle, retain traces of these unusual isotopic ratios. The detection of these nuclear technosignatures would be a monumental undertaking requiring specialized ultra-sensitive radiochemical analyses of ancient rock and sediment cores. Scientists would be looking for deviations from natural background radiation levels, specifically targeting the unique isotopic ratios characteristic of nuclear fission. For instance, the presence of technetium-99, an element with no stable isotopes and almost exclusively produced by fission, would be an undeniable marker. Its half-life of 211,000 years means that after millions of years, very little would remain, but even trace amounts, or its decay products in unusual concentrations, could be indicative if detected with sufficient precision. The geological context is also critical. A nuclear war signature would likely be concentrated within a relatively narrow geological time band, marking a singular cataclysmic event, rather than a gradual prolonged industrial build-up. This sharp global boundary layer would act as a clear event horizon in the geological record. Researchers would need to analyze samples from widely separated locations on Earth, looking for a synchronous and consistent pattern of these specific radioactive and chemical anomalies. The signal would have to be robust enough to survive diagenesis and metamorphism. While metamorphism could potentially alter the chemical form of isotopes, the ratios themselves, if locked into stable mineral matrices, might persist. Of course, distinguishing such an event from natural phenomena remains the paramount challenge. Earth has experienced several mass extinction events throughout its history, often linked to massive volcanic activity or asteroid impacts. These events leave dramatic geological markers, including widespread changes in climate, ocean chemistry, and the fossil record. However, the specific isotopic signatures of nuclear fission, particularly the transuranic elements and the unique ratios of certain fission products, would be distinctly different from anything produced by purely natural processes. The sheer scale and speed of radioactive fallout and the specific elemental cocktail it produces would be unique. An ancient nuclear war would offer the most unambiguous, though terrifying, proof of a pre-human industrial civilization. While other signatures might be ambiguous or explainable by natural variations, the fingerprint of atomic fission is fundamentally artificial. It represents a deliberate, conscious manipulation of matter on a scale that irrevocably alters the planet's fundamental composition for millions of years. Its discovery would not only rewrite Earth's history, but also serve as a profound ancient warning from a lost civilization that perhaps, like us, reached for the stars only to extinguish itself in a blaze of its own making. The silence of the deep past holds not just the secrets of creation, but potentially the echoes of self-destruction. Beyond the specific material traces or the horrific scars of nuclear conflict, a sufficiently advanced industrial civilization would inevitably exert a profound influence on its planet's climate and atmosphere. Our own human civilization is currently demonstrating this capability on a global scale, fundamentally altering Earth's atmospheric composition and energy balance, leading to what we term climate change. For the scientific detective searching for a pre-human industrial society, these planetary distress signals, anomalies in ancient climate records and atmospheric gas compositions offer a crucial large-scale avenue of investigation. The primary driver of modern anthropogenic climate change is the release of greenhouse gases, primarily carbon dioxide and methane, from the burning of fossil fuels and industrial processes. These gases trap heat in the atmosphere, warming the planet. A hypothetical ancient industrial civilization, relying on similar energy sources, would produce an analogous spike in greenhouse gas concentrations. The question is, could these ancient atmospheric signals be detectable millions of years later in the geological record? Ice cores, though rarely extending beyond 1 million years, provide pristine archives of past atmospheric gas concentrations. However, for deeper time, the evidence must come from other proxies. Carbon dioxide levels from millions of years ago can be reconstructed from various geochemical indicators in sedimentary rocks. For instance, the carbon isotopic composition of ancient soils and marine carbonates, as discussed in Block 2, can reveal shifts in the global carbon cycle. A rapid, sustained injection of abyssal, originating from the widespread burning of fossilized organic matter by an ancient civilization, would register as a distinctive negative excursion in the carbon isotope record, D13C. This Suez effect is a hallmark of our own industrial era and would be a powerful indicator of a similar past. Methane, another potent greenhouse gas, also leaves a fingerprint. Its carbon isotopic signature, D13CCH4, can distinguish between methane produced by biological processes, which tends to be very light, i.e. depleted in carbon-13, and methane from thermogenic sources, like natural gas leaks, or potentially industrial processes like methane cracking. A sudden, global increase in atmospheric methane from an industrial source could leave a detectable trace in the isotopic composition of carbon in contemporaneous sediments or ancient peats. However, methane is a less stable atmospheric gas than carbon dioxide, and its direct preservation over millions of years is more challenging, making proxies even more critical. Beyond specific gas concentrations, the rate and magnitude of climate change are key. Earth's climate naturally fluctuates over geological timescales, driven by orbital cycles, Milankovitch cycles, volcanic activity, and tectonic shifts. However, these natural changes typically unfold over tens to hundreds of thousands or millions of years, often with discernible cyclical patterns. An industrial civilization, rapidly releasing greenhouse gases, would likely trigger an abrupt, geologically instantaneous warming event, distinct in its speed and intensity from most natural climate shifts. Scientists looking for a Silurian civilization would search for a sharp, non-cyclical, globally synchronous warming spike in paleoclimate records that cannot be explained by known natural forcings. This would involve analysing oxygen isotope ratios in ancient marine fossils, which indicate past temperatures, examining changes in global sea levels, and looking for rapid shifts in sedimentary faces that point to dramatic environmental upheaval. The impact on the global hydrological cycle could also leave a mark. Rapid warming can intensify the water cycle, leading to more extreme precipitation events in some regions and prolonged droughts in others. These shifts might be evident in the geological record through changes in river deposits, ancient lake levels, or evaporate formations. The increased frequency of wildfires, another consequence of warmer, drier conditions and potentially industrial activity, could leave layers of charcoal and soot in sediment cores globally, distinct from the localized, less synchronous patterns of natural fires. The concept of ocean acidification also becomes relevant. As atmospheric carbon dioxide dissolves into the oceans, it forms carbonic acid, increasing the acidity of seawater. This process dissolves calcium carbonate shells and skeletons of marine organisms, leaving an undeniable signature in the fossil record. Our modern era is seeing a rapid decrease in ocean pH, threatening calcifying organisms. If a Silurian civilization released CO2 on a similar scale, the geological layers corresponding to that period might show a dissolution horizon, a boundary where the preservation of carbonate-shelled organisms dramatically declines, or their shells show signs of extensive corrosion. This would be a profound and long-lasting planetary distress signal. The challenge lies in differentiating these signals from the multitude of natural climate events that have punctuated Earth's history. The Paleocene-Eocene thermal maximum, PETM, around 56 million years ago, for example, was a period of rapid global warming, ocean acidification, and a significant carbon isotopic excursion. While often attributed to massive natural carbon releases, its rapidity and scale are sometimes cited as a possible natural analogue for the kind of event a Silurian civilization might trigger. However, the precise causes of events like the PEM are still debated. For a Silurian hypothesis, the key would be a climate signal without a clear natural explanation, especially if combined with other technosignatures like synthetic materials or nuclear fallout. The search for these ancient planetary distress signals requires global coordination and advanced analytical techniques. Paleoclimatologists would need to analyze samples from diverse geological settings, deep ocean sediments, ancient lake beds, terrestrial soil sequences, and fossilized reefs, using high-resolution proxies to reconstruct past atmospheric composition and climate conditions. They would build intricate models of Earth's past climate, running simulations to see if known natural processes can account for any observed anomalies. A significant, rapid, and unexplainable deviation from these natural baselines would be a powerful, albeit indirect, piece of evidence for a pre-human industrial civilization. It would mean that a prior intelligence, much like our own, inadvertently, or perhaps deliberately, pushed its home planet into a state of geochemical crisis, leaving a warning etched into the very fabric of Earth's history. This atmospheric archive, though subtle, could be one of the most enduring legacies of a lost world. The Earth's surface, as we've established, is a relentless shredder of history. Yet, beneath the churning waves and shifting continents, there lies a vast, comparatively undisturbed archive, the deep ocean sediments. These abyssal plains and trenches, often far from the destructive forces of erosion and tectonic uplift, accumulate layers of material over millions of years, acting as an unparalleled time capsule for planetary history. For the scientific detective on the trail of the Silurian hypothesis, these subduction-resistant regions offer the most promising, and perhaps only, reliable repository for the subtle technosignatures of a vanished civilization. Imagine the ocean floor as a colossal slow-motion conveyor belt. Material constantly rains down from the surface, microscopic marine organisms, fine dust from continents, volcanic ash, and dissolved chemicals precipitating out of seawater. This continuous gentle snowfall builds up layers of sediment, one on top of another, year after year, century after century. In the deepest, most tranquil parts of the ocean, where currents are minimal and biological activity is low, these layers can remain largely undisturbed for tens of millions of years, sometimes even hundreds of millions. They are the pages of Earth's most ancient diary, meticulously recording the planet's atmospheric composition, ocean chemistry, and even biological activity at the time of their deposition. Crucially, not all oceanic crust is destined for immediate subduction. While mid-ocean ridges constantly generate new crust that eventually plunges back into the mantle, vast regions of abyssal plain sediments, particularly in the older, colder parts of ocean basins, can persist for hundreds of millions of years before meeting their ultimate fate. Furthermore, certain unique geological settings such as accretionary wedges at subduction zones, where sediments are scraped off the subducting plate and piled up, or abducted oceanic crust that becomes thrust onto continents, can preserve fragments of very ancient ocean floor and its sedimentary record. These rare, geologically stable pockets are precisely where researchers would focus their efforts. The information density within these sediment cores is astonishing. Scientists can extract long cylinders of sediment, sometimes kilometers in length, representing continuous records spanning vast geological epochs. Each centimeter of core can correspond to thousands of years of Earth's history. By analyzing the chemical, isotopic, and paleontological composition of these layers, a comprehensive picture of past environments emerges. This is where the hunt for industrial civilization's echoes truly begins. Consider the potential for isotopic anomalies, as previously discussed. A massive input of carbon-13 depleted carbon dioxide from the burning of fossil fuels would dissolve into the ocean, altering its carbon isotopic signature. Marine organisms, particularly those that build carbonate shells like foraminifera, would incorporate this altered carbon into their structures. When these organisms die, their shells rain down onto the seafloor, becoming part of the accumulating sediment. Analysing the D13C of ancient foraminifera shells within a sediment core could reveal a sharp negative excursion, a global signal of industrial carbon emissions tens of millions of years ago. Similarly, shifts in nitrogen and sulfur isotopes from synthetic fertilizers or industrial pollution would be recorded in the chemical composition of the sediment layers. The deep ocean is also a potential graveyard for technofossils. While macroscopic plastic objects would degrade, microscopic fragments and their chemical degradation products could be incorporated into marine sediments. In anoxic, oxygen-depleted deep-sea environments, organic matter is preserved with much greater fidelity, slowing decomposition. If ancient microplastics or other synthetic residues were deposited in sufficient quantities into such anoxic basins, they might survive, albeit chemically altered, as unique organic compounds or mineral inclusions within the sediment. Identifying these molecular fossils of technology would require highly advanced organic geochemistry techniques, searching for complex non-biogenic organic molecules with specific bonding structures or elemental ratios that cannot be explained by natural processes. Even the consequences of an ancient nuclear war would find their ultimate resting place in these deep-sea archives. The fine dust and radioactive fallout from such an event would settle out of the atmosphere and ocean column, accumulating as a distinct, globally distributed layer within the sediments. This layer would be characterized by anomalous concentrations of specific fission products, such as plutonium isotopes or technetium-99, along with unique elemental ratios from vaporized materials. While the sheer age would mean extreme dilution, ultra-sensitive mass spectrometry could potentially detect these subtle, long-lived radioactive fingerprints, differentiating them from natural background radiation or extraterrestrial impacts. The search methodology involves an intricate dance between geology, oceanography, and analytical chemistry. Ocean drilling programs like the International Ocean Discovery Program routinely collect such cores from around the world. Researchers select specific geological horizons corresponding to the time frame of interest for the Silurian Hypothesis, then subject samples to an array of tests. This includes high-resolution elemental analysis, stable isotope geochemistry, organic biomarker analysis, and potentially cutting-edge radiochemical assays for long-lived anthropogenic radionuclides. The challenge is immense, requiring the ability to detect incredibly subtle signals against a noisy background of natural planetary processes spanning millions of years. The key to success lies in identifying multiple corroborating lines of evidence from these deep-sea archives. No single anomaly would be definitive. A localized isotopic spike could be explained by a natural event. A peculiar organic compound could be an unknown natural biomarker. But if researchers were to find a globally synchronous layer in deep-sea sediments, exhibiting a carbon isotopic excursion consistent with fossil fuel burning, alongside unusual nitrogen and sulfur isotope ratios suggesting synthetic fertilizers, and perhaps microscopic residues of non-biogenic polymers, all within the same geological horizon, then the case for a pre-human industrial civilization would become compelling. The deep ocean, silent witness to eons of Earth's history, holds the potential to reveal a secret far more profound than any sunken city. The truth of a civilization lost not to memory, but to the crushing embrace of geological time itself. While our primary investigation into the Silurian Hypothesis focuses on Earth's deep past, the vast cosmic theatre provides an unexpected yet invaluable lens through which to refine our search. The burgeoning field of exoplanet research, specifically the hunt for biosignatures and technosignatures on worlds beyond our solar system, offers a powerful framework for understanding what traces a distant or ancient civilization might leave behind. By examining how we propose to detect life and technology across interstellar distances, we can develop more sophisticated strategies for identifying similar, long-buried evidence on our own planet. Consider the ongoing quest for extraterrestrial life. Astronomers design next-generation telescopes like the James Webb Space Telescope and future observatories to analyze the atmospheric composition of exoplanets. They search for biosignatures, gases like oxygen, methane and water vapor in proportions that are highly unlikely to arise from abiotic, non-biological processes. The presence of oxygen, for example, especially when paired with a reducing gas like methane, is a strong indicator of widespread photosynthetic life. as oxygen is highly reactive and quickly removed from an atmosphere without constant replenishment. This concept of looking for disequilibria in planetary atmospheres, chemical imbalances that require a constant input of energy from life, is directly applicable to our search for ancient earthly civilizations. For the Silurian Hypothesis, this means we should be looking for ancient atmospheric disequilibria that are technological in origin rather than biological. For example, a sudden sustained spike in non-natural industrial gases or ratios of gases that defy known geological and biological cycles would be a compelling technosignature. While ancient atmospheres cannot be directly sampled, proxy records in deep-sea sediments and ice cores, as discussed in Block 6, can reveal these shifts. If an ancient civilization released vast amounts of nitrogen oxides or chlorofluorocarbons, CFCs, gases that have no significant natural sources, into the atmosphere, these highly unusual chemical fingerprints, even if decayed or altered, might still leave detectable residues or isotopic changes in the geological record. The key insight from exoplanet studies is to look for anomalous chemical states that require an intelligent, energy-intensive process to maintain. Furthermore, the search for technosignatures on exoplanets extends beyond mere atmospheric gases. Astronomers speculate about detecting artificial illumination from city lights on the night side of exoplanets, or industrial pollution plumes, or even megastructures like Dyson spheres. While these are direct observational targets for distant worlds, on Earth, their ancient equivalents would be indirect. The lesson here is about scale. If an ancient civilization had a global energy footprint comparable to ours, its impact on Earth's energy budget and atmospheric chemistry would have been profound and measurable. A global warming event driven by industrial greenhouse gases, a widespread alteration of the carbon cycle, or the deposition of non-natural industrial pollutants into sediments. These are the earthbound equivalents of a distant technosignature. The perspective from exoplanets also highlights the importance of false positives. Just as a seemingly promising atmospheric biosignature on an exoplanet might ultimately be explained by unusual geological processes, e.g., non-biological sources of oxygen, so too must we be vigilant against natural explanations for any potential technosignatures on ancient Earth. Earth's geological history is replete with dramatic planet-altering events, supervolcano eruptions, asteroid impacts, and episodes of extreme climate change. Each of these can leave significant chemical and isotopic scars. The challenge is to differentiate these powerful natural events from the specific, unique fingerprints of industrial activity. This requires establishing robust baselines of natural planetary evolution, then meticulously searching for deviations that cannot be reconciled with known natural phenomena. For instance, the detection of unusual metallicity in an exoplanet's atmosphere, or a sudden, unexplained depletion of a rare element in its crust, might suggest advanced mining or engineering. On Earth, this translates to searching for unusually concentrated deposits of rare earth elements or other industrially critical metals in ancient sedimentary or metamorphic rocks, especially if their distribution or isotopic ratios defy natural geological processes. If a pre-human civilization engaged in large-scale extraction and processing of metals, it would inevitably alter the distribution and isotopic composition of these elements within the Earth's crust, creating a long-term, albeit subtle, geological anomaly. Moreover, the Great Filter concept, often discussed in the context of extraterrestrial intelligence, implicitly informs the Silurian Hypothesis. The idea that there are filters or obstacles preventing life from developing into advanced civilization might apply to Earth's own deep past. Could a previous civilization have failed to cross a critical threshold, or perhaps encountered a catastrophic self-imposed filter? An ancient nuclear war, for example, would be a catastrophic filter. The search for its traces on Earth would be a direct investigation of such a filter in our own planetary history. This cosmic perspective helps us frame the search not just for the presence of a civilization, but also for the reasons for its disappearance. Ultimately, the study of exoplanets teaches us to think globally and systematically about planetary change. It compels us to consider the full range of potential signatures, from the subtle to the catastrophic, and to develop interdisciplinary methods for their detection. The techniques and mindset employed to hunt for distant technological life are the very same tools we can turn inward upon our own planet to uncover secrets buried deep within its ancient geological layers. It's a humbling realization. The very methods we use to scan the universe for others might, in fact, be our best hope for discovering our own planet's forgotten past. The universe provides a mirror, reflecting back the questions we must ask of ourselves and our planetary home. Our journey into Earth's deep past, searching for the ghost of a pre-human industrial civilization, leads us paradoxically back to our present moment. The most potent tool in this scientific detective's arsenal is not an ancient artifact, but a stark and undeniable reality, the Anthropocene echo. By meticulously examining the global impact of our own civilization, the unmistakable geological fingerprints we are currently embedding into the planet, we gain an unparalleled model for what to search for when investigating the Silurian Hypothesis. We are, in effect, performing a real-time experiment, crafting the very techno-signatures that future geologists millions of years hence might uncover and debate. The Anthropocene, a proposed new geological epoch, is defined by humanity's profound and pervasive impact on Earth's geology and ecosystems. Our industrial activities, spanning little more than 2 centuries, have already left an indelible mark that will be visible in the stratigraphic record for millions of years. This human layer serves as a direct, empirical guide for understanding the scale and character of anomalies a hypothetical Silurian civilization might have left. What we're doing today is exactly what we are looking for in the deep past. Consider the carbon isotopic anomalies. Since the dawn of the Industrial Revolution, our burning of fossil fuels has released vast quantities of ancient, has caused a measurable decrease in the D13C signature of the atmosphere, oceans, and consequently, in newly forming organic matter and carbonate sediments globally. This Suez effect is a globally synchronous, unequivocal signal of our industrial activity. If a Silurian civilization had a similar energy economy, a comparable negative D13C excursion in the ancient geological record would be a powerful, direct analogue to our Anthropocene. Geochemists are now meticulously documenting this modern shift, creating a robust comparative data set. Next, consider technofossils. Our era is characterized by the widespread production and dispersion of novel synthetic materials, most notably plastics. These durable polymers are accumulating in landfills, permeating oceans, and fragmenting into microplastics that are being incorporated into sediments worldwide. Scientists are studying the degradation rates and long-term fate of these materials, understanding how they might transform over geological timescales. The plastic layer in future sediments will be a distinct, unprecedented marker. If an ancient civilization produced analogous long-chain polymers or other highly engineered materials, even if degraded into their constituent molecules or microparticles, their unusual chemical signatures or elemental compositions, locked within ancient sediments, would be the ancient equivalent of our modern plastic pollution. The Anthropocene teaches us what specific organic and inorganic chemical signatures to hunt for. Our industrial agriculture, fueled by synthetic nitrogen fertilizers from the Haber-Bosch process, has fundamentally altered ecosystems, leads to widespread eutrophication, creating anoxic dead zones in coastal waters and leaving distinct nitrogen isotopic signatures in sediments. The scale of this planetary engineering for food production is unparalleled in natural history. If a Silurian civilization achieved similar agricultural output, we would expect to find a comparable, globally synchronous signal of altered nitrogen isotopic ratios, alongside evidence of widespread anoxic events in ancient marine sediments driven by excess nutrient runoff. Our current impact provides a clear template for what constitutes an industrial agricultural signature, and tragically the spectre of nuclear conflict. The handful of atmospheric nuclear tests conducted in the mid-20th century, though minuscule compared to a full-scale war, released unique radionuclide signatures, e.g. specific plutonium and cesium isotopes, into the global environment. These short-lived traces are already diminishing, but the potential for long-lived fission products or characteristic isotopic ratios to persist in the geological record serves as a grim template. A future global nuclear exchange would leave a far more profound and enduring isotopic and geological scar. This modern, albeit limited, nuclear fingerprint provides a direct guide for identifying the specific, non-natural isotopic anomalies that would characterize an ancient atomic conflict. Furthermore, the Anthropocene is defined by rapid, large-scale shifts in biodiversity and ecosystem function. We are witnessing mass extinctions, the global redistribution of species, and profound changes in ecological interactions. While natural mass extinction events have occurred throughout Earth's history, the current rate and the specific drivers, habitat destruction, pollution, or climate change, are unique. If a Silurian civilization similarly dominated its biosphere, we might expect to find corresponding highly unusual patterns in the fossil record: rapid, non-natural species turnovers, the widespread introduction of domesticated species, or the disappearance of native flora and fauna at the relevant geological horizon. The Anthropocene is not just a geological concept, it is a profound philosophical challenge. It forces us to acknowledge our immense power to shape the planet and, by extension, to consider the possibility that others might have done so before us. By studying our own footprint, we are building the scientific lexicon and the analytical toolkit necessary to identify similar impacts from a deep-time predecessor. Every plastic bottle, every ton of CO2 emitted, every acre of deforested land is not just altering our present, but also writing a chapter in Earth's deep future, simultaneously creating a reference standard for the ancient past. The great irony of the Silurian hypothesis is that humanity, in its own industrial fervour, is inadvertently illuminating the path to discovering its potential predecessors. We are actively creating the very geological and chemical anomalies that we are now learning to detect millions of years later. Our current era serves as a living laboratory, a guide to the kinds of planetary-scale technosignatures that are robust enough to survive the grand erasure and stand as a testament to intelligent life. The Anthropocene echo is therefore not just a reflection of our present, but a crucial Rosetta Stone for deciphering Earth's hidden past. Our scientific detective journey through Earth's deep time, seeking the ghostly fingerprints of a pre-human industrial civilization, culminates in a profound conceptual challenge known as the Great Filter. This idea, originally conceived in the context of the Fermi paradox, the unsettling silence in a seemingly crowded universe, takes on a unique and chilling relevance when applied to our own planet's history. The Silurian hypothesis forces us to consider if Earth itself harbours a hidden Great Filter, a catastrophic obstacle that intelligent technological civilizations repeatedly encounter and often fail to overcome, leaving only the faintest geological whispers of their passage. The Great Filter posits that there is some immense barrier or series of barriers that makes the emergence of intelligent, spacefaring life exceedingly rare. This filter could be in our past, making life itself rare, or the evolution of intelligence rare, or in our future, making advanced civilizations inherently self-destructive or prone to collapse. If the Silurian hypothesis were confirmed, meaning an advanced civilization rose and fell on Earth millions of years ago, it would profoundly shift our understanding of where the Great Filter might lie. If such a civilization existed and vanished, it would suggest that the filter isn't necessarily in the initial emergence of intelligent life, but rather in its long-term survival. It would imply that technological civilizations, once they reach a certain level of industrialization, are inherently unstable or face existential threats they cannot overcome. An ancient nuclear war, for example, would represent a catastrophic self-imposed filter, a stark warning from the deep past. A civilization that collapses due to unsustainable resource consumption, irreversible climate change, or ecological collapse, leaving behind only the planetary distress signals we discussed, would also signify a powerful internal filter. The concept of cosmic cycles adds another layer to this interpretation. Earth has undergone dramatic transformations over its 4.5 billion year history. Ice ages, supervolcanic eruptions, asteroid impacts, shifts in atmospheric composition, and profound changes in ocean chemistry. Could some of these natural planetary cycles act as external filters, wiping the slate clean and resetting the evolutionary clock, allowing intelligent life to emerge only to be periodically extinguished? For instance, a prolonged snowball Earth event or a period of intense volcanism might make the sustained existence of an industrial civilization impossible. The detection of a planetary-scale technosignature, abruptly terminating at a geological boundary associated with a major environmental upheaval, could point to such a cosmic filter at work. Conversely, the Silurian hypothesis could also imply a softer filter, one that merely makes the detection of past civilizations incredibly difficult. The grand erasure of geological time itself could be the primary filter, ensuring that even thriving civilizations leave behind only ambiguous, ephemeral traces. If Earth is constantly recycling its surface, burying and destroying evidence, then the filter isn't necessarily one of existence, but of archaeological visibility. This would mean that intelligent life might be more common, but its long-term record is almost always lost to the planet's relentless geological metabolism. In this scenario, we might be living on a graveyard world, having inherited a planet that has hosted multiple successive intelligent species, each erased by time. The implications for humanity's future are stark. If the Silurian hypothesis is true, and such a civilization met its end due to self-destruction or environmental collapse, it serves as an ancient mirror reflecting our own present challenges. Our current impact on the planet, meticulously documented as the Anthropocene echo, is precisely the kind of planetary distress signal that would precede a collapse. The search for ancient isotopic anomalies, technofossils and climate shifts is, therefore, not just an academic exercise in paleontology or geochemistry. It is a search for an ancient warning, a cautionary tale from our own world that speaks to the fragility of technological societies. If we do find evidence of a past industrial civilization on Earth, it wouldn't necessarily solve the Fermi paradox. Instead, it would localize a great filter, right here, under our feet. It would mean that reaching technological capability is not enough. Sustained, long-term survival is the true challenge. Such a discovery would force us to seriously re-evaluate our own trajectory and the sustainability of our industrial practices. It would compel us to ask, are we repeating an ancient mistake? Are the planetary distress signals we are currently generating merely an echo of a previous demise? The absence of evidence is also profoundly informative. If, after rigorous investigation, no compelling technosignatures or isotopic anomalies are found in the geological record, it strengthens the argument that humanity might indeed be Earth's first industrial civilization. This would mean the Great Filter is likely somewhere in the past, evolutionary steps leading to our emergence, making intelligence itself a rare phenomenon. It would place a heavier burden on humanity to be the custodians of this rare intelligence, to ensure our civilization avoids becoming a future geological ghost. Ultimately, the Silurian hypothesis, intertwined with the Great Filter, forces us to confront uncomfortable truths about intelligence, survival, and the destiny of technological species. It transforms our planet into a cosmic laboratory, an arena where intelligence might have risen and fallen multiple times, each cycle leaving its subtle, almost imperceptible mark. Whether Earth has hosted a forgotten civilization or not, the scientific investigation itself sharpens our awareness of our own impact and prompts us to consider the long-term legacy we are forging for future generations, and indeed, for the planet's deep future. The search for ancient planetary scars is, at its heart, a profound meditation on humanity's place in the grand, cyclical story of life and intelligence in the universe. Our journey into the profound depths of Earth's history, guided by the audacious Silurian hypothesis, has been a scientific detective investigation of the highest order. We began with a seemingly fantastical question. Could an industrial civilization have risen and fallen on our own planet, millions of years before humanity's dawn? This inquiry, far from being mere speculation, has revealed itself as a rigorous exercise in geochemical forensics and deep-time thinking, pushing the boundaries of what we consider possible. We've sifted through the planet's silent archives, examining the formidable challenge posed by the Grand Erasure, the relentless geological processes of plate tectonics, erosion, and metamorphism that conspire to obliterate almost all traces of transient life, let alone technology, over eons. This understanding immediately reframes our search. We cannot expect to find ancient ruins or recognizable artifacts. Instead, our quarry must be the most enduring planetary-scale signatures, etched not in stone monuments but in the very chemistry of Earth itself. Our investigation then turned to the subtle yet profound shifts in isotopic ratios, the chemical fingerprints of industrial activity. The burning of fossil fuels by an ancient civilization would have left a distinct carbon-13 depletion in ancient sediments, a Suez effect echoing our own Anthropocene. Similarly, the widespread use of synthetic fertilizers would have perturbed the global nitrogen cycle, leaving anomalous nitrogen isotopic signatures in deep-sea cores. Even industrial pollution, like unique sulfur isotopic patterns from smelting, would have embedded itself into the geological record. These are the whispers of a lost industry, diffused across continents and oceans, waiting for our sophisticated mass spectrometers to detect them. The possibility of technofossils, such as long-degraded plastics or specialized ceramics, further expanded our search. While direct identification of intact synthetic materials from millions of years ago is highly improbable, their chemical degradation products or unique molecular ghosts, particularly if preserved in anoxic deep-sea sediments, could still bear the unmistakable mark of artificiality. Such a discovery would demand a rigorous differentiation from natural organic compounds, pushing the limits of analytical chemistry. Most chillingly, we confronted the potential for an ancient nuclear war, a planetary scar of self-destruction. The unique isotopic ratios of fission products, the global fallout layer of iridium-rich soot without impact evidence, and the profound, abrupt climate shifts of a nuclear winter would constitute an almost undeniable technosignature. While the long half-lives of some radionuclides make direct detection challenging over eons, the specific elemental cocktail and the precise isotopic ratios of fission are fundamentally artificial, offering a terrifyingly clear signal if it exists. We explored the planetary distress signals, the long-term consequences of an industrial civilization's impact on climate and atmosphere. A rapid, unexplainable spike in greenhouse gases, evident through carbon and oxygen isotope proxies, combined with widespread ocean acidification and synchronous anoxic events, would paint a picture of an ancient world pushed to its geochemical limits. These global environmental shifts, distinct from natural geological cycles, offer a powerful, large-scale avenue for detection. The crucial role of subduction's archive became evident. Deep ocean sediments, particularly those in subduction-resistant basins, emerge as the primary repository for these elusive technosignatures. Undisturbed layers of abyssal clay and microfossil-rich oozes preserve continuous records of Earth's past chemistry, making them the most promising hunting grounds for isotopic anomalies, molecular technofossils, and nuclear fallout. Our perspective was sharpened by lessons from exoplanets, the methods we developed to search for biosignatures and technosignatures on distant worlds, looking for atmospheric disequilibria, industrial pollutants, or anomalous elemental distributions, provide a powerful conceptual framework for our terrestrial hunt. By understanding what makes a distant alien civilization detectable, we gain insight into what a profoundly ancient one on Earth might have left behind. And finally, the Anthropocene echo provided our most profound real-time model. Our own civilization is currently depositing an indelible, human layer into the geological record. The Suez effect in carbon isotopes, the ubiquitous plastic layer, the global nitrogen fertilizer signal, and even the faint but real radionuclide traces from nuclear tests. By meticulously documenting our own impact, we are creating the very Rosetta Stone that future, or ancient geologists, would need to decipher an older, lost civilization. What, then, is the ultimate meaning of this scientific quest? Even if we find no definitive evidence of a pre-human industrial civilization, the journey itself is profoundly transformative. It forces us to critically re-evaluate our place in planetary history, moving beyond an anthropocentric view where humanity is the sole, singular technological awakening. It humbles us, reminding us that the vastness of geological time can easily swallow empires, leaving barely a trace. The absence of evidence in this context does not necessarily prove absence, but highlights the immense destructive power of time and geological processes. Conversely, if even the slightest, most subtle, yet unequivocally artificial technosignature were detected, a global isotopic anomaly without a natural explanation, a specific molecular fingerprint of a synthetic material, or the chilling signature of ancient fission, it would be one of the most paradigm-shattering discoveries in history. Its life and intelligence on Earth. It would imply that the great filter, if it exists, is not necessarily in the emergence of intelligence, but in its longevity or its detectability across eons. It would transform our understanding of cosmic evolution, suggesting that perhaps intelligence is not as rare as the Fermi paradox implies, but rather its long-term persistence or its ability to leave enduring, decipherable marks also carry a profound ancient warning. If a prior civilization rose and fell on Earth, its fate could be a mirror reflecting our own potential future. Did it collapse under the weight of its own industrial impact, succumb to climate change of its own making, or tragically extinguish itself in an ancient nuclear fire? In the Anthropocene might be echoing a previous demise, a cycle of rise and fall etched into the very fabric of our homeworld. This thought, while unsettling, imbues our current environmental and geopolitical challenges with an almost sacred urgency. We are not just shaping our future, we are writing a potential chapter in Earth's deep past for a future generation, human or otherwise, to uncover. The Silurian Hypothesis is more than a thought experiment. It's an invitation to think beyond our human-scaled perception of time and history. It challenges us to imagine intelligence in forms, and at times we rarely consider, forcing us to ask, what would it take for us to be detected millions of years from now? What enduring legacy are we truly building? This inquiry makes us better geologists, better chemists, and perhaps better stewards of this extraordinary ancient planet. It reminds us that Earth is not merely our home, but a vast living archive, holding secrets that could redefine everything we know about life's journey through the cosmos. The universe is a grand, unfolding story, and perhaps Earth has already told some chapters we are yet to truly read.